Hi everyone, my name is Mu Wei Wei, and today I'll be presenting question 2 and question 7 for the computer-based test of Stochastic Calculus for Financial Economics. So to start off, I'll be presenting question 2 first. For question 2, cooperative food stock has a current price of $35. Its annual volatility is 20%. The stock pays dividends continuously at a rate of 2%. Exercise is only permitted on the expiry date. The continuously compounded risk-free interest rate is 6% per annum. The stock price at the end of every month are simulated using the following 0 to 1 uniform random numbers. So first of all, a 48-month Asian average strike call option on cooperative food stock uses an arithmetic average based on the stock price at the end of each of the 1 month. So we have to determine the current price of the option. We start off by writing down the information that is given by the question. So current price of $35 is S0 equals to 35, and volatility 20% means that the sigma equals to 0.2. Pays dividends continuously at a rate of 2%, the delta equals to 0.02. The continuously compounded risk-free interest rate is 6%. That means R equals to 0.06. So part 1 asks us to find for a 48-month Asian average strike call option. So that means the T in months is 48, and the smaller T is every month. So it's 1 divided by 12. And the T in years is 48 divided by 12 equals to 4 years. Then I create a column to list down the values of T for every month. So T starts from 0 until 48. And then for the uniform random numbers for the stock price at the end of every month is given here. So this is U, and I just type out the values for U from T equals to 1 to 48. And then for the corresponding z-scores, I use the inverse standard normal function to find the z-score for the corresponding U. So I use this formula, and then I just drag down to all the cells below. To find ST, I use this formula right here. So which is ST equals to S0 times the exponential of R minus delta minus 0.5 sigma squared times T plus sigma square root T times Z score. So S0 is given in the question, which is the current price of $35. So equals to this cell right here. But when T equals to 1, it is going to follow this equation right here. So S0 times the exponential of R minus delta minus 0.5 times sigma squared times small t plus sigma times the square root of small t times the corresponding z-score. And then I also drag this formula down to the following values to get the ST for each month. Since the first part of the question asks us to use the arithmetic average for the call option, so we create a column for AT, which is the arithmetic average for each values of T. So arithmetic average is basically the average for ST. So when T equals to 1, it is basically the average of S1. So it should be the same value as S1. But when T equals to 2, it is the average of S1 and S2. So it would be 37.9419. And then when T equals to 3, it will be the average from S1 to S3, and so on. So we just drag this formula down to the following cells, and we'll get the AT for each values of T. So what we need is A48. So it will be this value right here, which is 59.9579. And then we find the expected payoff at t equals to 48, because when we find the current price of the option, we will be using this equation right here, which is v equals to exponential negative rt times the expected payoff at t. So to find the expected payoff at t equals to 48, it is the difference between S48 and A48, which is ST minus AT. So S48, we can take the value here, which is 65.2489, minus A48, which is 59.9579. The reason we're using the max function right here because we only want it to return a positive value. So if the difference is a negative value, it will simply return 0 instead. So the expected payoff at t equals to 48 is 5.2909. Lastly, we find the current price of option, which is by using the equation right here. So exponential negative r times t times the expected payoff at t, which is in the cell right here, we get the price is 4.162. For the second part of this question, we are given a 48-month 36-strike geometric average price put option on cooperative food stock. The geometric average is based on the stock prices at the end of each month. So we have to determine the current price of the option. From the question, a 36 strike means that K equals to 36. So to get the geometric average is the product of ST to the power of 1 over T. So when T equals to 1, the geometric average would be the product of S1 to the power of 1 over 1. So it should also be the same value as S1, which is 35.681. But when T equals to 2, it would be the product of S1 and S2 to the power of 1 over 2. So we get the value of 37.8745. And when T equals to 3, it will be the product of S1, S2, and S3 to the power of 1 over 3. And we'll get the value of 39.6993. So this is the same for the following cells, and we should be able to get the geometric average for each values of T. So what we need is G48 right here. So G48 equals to 59.2114908. Since it is a geometric average price put option, we get the expected payoff by minusing G48 from K. So we use the max function, and then we find the difference between K and G48. And since we only want it to return a positive value, so we put 0 here. So if it's a negative, it will return 0. Since G48 is larger than the value of K, we get 0 as the expected payoff at T equals to 48. And then we use the same equation right here to get the current price of this option. And since the expected payoff is 0, we should get the price of the option is also 0. So that is all for question 2. Next, I'll be explaining question 7 for this CBT. For question 7, Tamara Mellon, a London-based fashion designer, is expecting to receive 100 million yen from a Japanese company as payment for goods sold in 1 year. Concerned about potential exchange rate fluctuations, the company decides to hedge its currency risk by purchasing an option that grants the right to exchange yen for pounds at the rate of 0.0055 pounds per yen. Given the following information, the spot exchange rate is 0.005 pounds per yen. The volatility of the exchange rate between two currencies is 0.08. The continuously compounded risk-free interest rate for yens is 0.055. The continuously compounded risk-free interest rate for pounds is 0.035. The first part of the question is asking us to calculate the cost of hedging using a 12-period binomial tree using two distinct approaches, pound-denominated and yen-denominated. Again, we start off by writing down the information given by the question. So the right to exchange yen for pounds at a rate of 0.0055 pounds per yen is K. K equals to 0.0055. And the spot exchange rate is X0, so X0 equals to 0.005. The volatility of the exchange rate is sigma, so sigma equals to 0.08. Compounded risk-free interest rate for yens is 0.055. So in this case, for pound denominated, the pound is the domestic currency while the yen is the foreign currency. So the risk-free interest rate for yens is the foreign risk-free interest rate. So the RF is 0.055 while the R is 0.035 since pounds is the domestic currency. And then the H is 1 divided by 12 since it is count as a year. And then for the up equation is U equals to exponential R minus delta times H plus sigma times the square root of H. So exponential of R minus delta. In this case for currency, delta is the foreign risk-free interest rate. So the delta is 0.05 times H plus sigma times the square root of H. So the U is 1.0216586 for pound denominated, and the down is the same as U, but we minus instead of plus. So the D is exponential R minus foreign interest rate times H minus sigma times the square root of H. So the D is 0.9755434. Next, the risk-neutral probability up, P star, is given by the equation right here. So P star equals to exponential R minus delta times H minus D divided by U minus D. So P star equals to exponential R minus the foreign risk-free interest rate times H minus D divided by U minus D. So for P star, we get 0.4942268. And the Q star is 1 minus P star, so it is 0.50577732. By using the information we got from the pound denominated, we will now generate a 12-period binomial tree for the exchange rate first. So when the period is at 0, it will be the spot exchange rate, which is 0.005. And for the first period, it will be right here, and this will be the up node, and this is the down node. So the up node is basically this value right here, the spot exchange rate times U, and the down node is this value times D. But looking at this formula, first we look at the cell in front of it. If this cell is empty, we will look at the cell above it. And if this cell is also empty, then it will return an empty cell. But if this cell has a value, then this will be the down node for this cell right here, and the formula will times the value in this cell right here with D. But if there's a value in the cell right here, it will times U, and this will become the up node for this cell right here. So in this case, since we are getting the up node for 0.005, the formula will end up timing the 0.005 with U. So we get the up node is 0.0051083. The formula is the same for the down node, but in this case, since the cell in front of it is an empty cell, it will look at the cell above it. So this cell has a value. So according to this formula, it will times the value in this cell with D. So this will be the down node for this cell right here. So the down node for the first period will be 0.0048777. And then we use the same formula for the following periods. Basically just drag it. So we should be able to get the 12-period binomial tree for the exchange rate right here. Afterwards, we construct a 12-period binomial tree for a put option. So why are we using a put option? Because for pound denominated, we can think of selling the yen to receive pound. So selling is a put option. And for this binomial tree, instead of starting from the front, we start at the back because we want to get this value right here. So for the 12th period, for put option, it is k minus st. So we use the max function to find the difference between the k and the value right here. So we use the max function because we only want it to return a positive value. So if it is a negative value, it will return it as 0. So we can see that it returns as 0 for this cell right here. And then the same goes for the following cells below. And we can see that it starts to return a positive value for these nodes right here. Starting from the 11th period, we use the if function again to find the values for these cells. So how do we get the value here? It is the risk-neutral probability up times the value in this cell right here, plus the risk-neutral probability down times the value right here. And then we times this value with the discount factor, which is exponential negative RH. So it's exponential negative RH. But when the cells right here are empty cells, it will simply return an empty value. So for the first node right here, it will be 0, since these values are also 0. But when we look at this cell right here, since this cell has a value, it will be this value times the risk-neutral probability down, and then times the discount factor. So for this node, we will get this value. And the formula is the same for all the cells in front here. So in the end, we will get this value at period 0, which is the price of the put option at the period of 0. So at last, the cost of hedging for the pound denominated will be the price of the put option times 100 million, which is the value right here. So next, we find the cost of hedging for yen denominated. So for yen denominated, the k will be 1 divided by 0.0055. This is because we want to express the value of 1 pound in terms of yen. And the spot exchange rate will also be 1 divided by 0.005. The volatility remains the same as 0.08. And the risk-free interest rate, since it is yen denominated, the domestic currency will be the yen, while the foreign currency will be the pounds. So the domestic risk-free interest rate is the yens, which is 0.055, while the foreign risk-free interest rate will be the pounds, which is 0.035. So the hedge remains the same, and the UD and the risk-neutral probabilities will use the same formulas, but the values will change because the values up here are also different. So the same as above, we generate a 12-period binomial tree for the exchange rate, but this time we use the values for the yen denominated. The formulas will be the same. And then we generate a 12-period binomial tree for the call option. In this case, we use a call option because we can think of it as buying the pounds with yen. So it will be a call option. The formulas will also be the same, but in this case, since it is a call option, it will be ST minus K. So it will be the exchange rate minus the K right here. And we also want it to return as a positive value, so we use the max function. So the formulas will be the same for this column for the 12th period. And then for the 11th period, it will also be the same as when we calculated the one for the pounds denominated. We use the if function to get these values right here. And this will be the same formulas. So in the end, we will get the price of the call option is 21.533197. So lastly, to get the cost of hedging for the yen denominated, it is similar to above. But in this case, since we want to express the value of £1 in terms of yen, so we also need to divide this 100 million with K. And then after dividing, we times it with the price of the call option. So the cost of hedging, we will get 11,843,258.57. So that will be all for the first part of question 7. And then onwards to the second part, we are required to calculate the price of the option by conducting a Monte Carlo simulation of 100,000 iterations using Microsoft Excel. And we also assume that the Black-Scholes framework is applied to the currency exchange rate. So for the second question, we will be using the values for the pound denominated. And for this one, we will be using the put option since it is pound denominated. So first, I start off by generating a sequence until 100,000 since the question wants 100,000 iterations. So I use the fill function right here, series. The set value will be 1 and the stop value will be 100,000 and the series will be generated in columns. So this will help to generate 100,000 columns for this part here. And then for the U, since we want to simulate it, we will use the random function to generate random numbers for the U. So just use the random function and drag it until the 100,000 cell. So it should help to generate 100,000 values for U. And then the corresponding z-score for the U, we will use the inverse standard normal function right here. And also to generate the z-score for the corresponding U. Next, to get the exchange rate, since it follows a Black-Scholes framework, so we can use the equation right here, which is xt equals to x0 times the exponential of r minus rf minus 0.5 sigma square times t minus t plus sigma squared of t minus t times the z-score. So for the first exchange rate, it will be x0 times exponential r minus the foreign risk-free interest rate minus 0.5 times sigma square times the t minus t plus sigma times the square root of t minus t times the corresponding z-score. So the formula should be the same for the following cells, and we should get each of the exchange rate. Next, we need to get the payoff for each of the values here, because to get the price of the option, it is similar to question 2, where we need to get the expected payoff. So to get the payoff, since this is a put option, so we use k minus xt, and we also use the max function to get the payoff. So for this one, it is k minus xt, the exchange rate. And we also only want the positive value, so that's why we use the max function. And then the expected payoff will just be the average of the payoff from the first payoff to the 100,000 payoff. So the expected payoff would be this value right here. And lastly, to get the price of the option, we times the expected payoff with exponential negative r times t minus t. But we also have to times 100 million as mentioned in the question right here. So in the end, we should get the price of the put option is 59,209. So that is all for question 7. I hope you enjoyed the video, and thank you.